elements. I want to go through a couple of exceptions to our Lewis structure theory and why Lewis structures don't always work. There is a class of molecules called radicals. A typical example is NO, not no, nitrogen monoxide. Radicals are investigated, no double O there, nitrogen monoxide, are investigated in organic chemistry. They are investigated in biochemistry as well. Free radicals in our body, things that are bad, that we could inhale, polycyclic aromatic hydrocarbons, PAHs, are a byproduct of combustion, so cigarette smoke or car exhaust has a lot of PAHs. These PAHs can get into our lungs and then cause radical reactions with our tissue, with our DNA. And so if you've ever heard of antioxidants or free radicals or that whole class of why you should eat blueberries or acai berries or any of those things, it's to mitigate any of these side reactions from these PAHs or from other things in our atmosphere that can cause distress in our systems, such as things like cancer. Radicals don't work for Lewis theory. Why? Well, if we think about nitrogen and oxygen making a molecule, there's no central atom because there's only two elements here. But once we start thinking about adding up our valence electrons, big old shock. What do we do with 11 electrons? Lewis doesn't know how to deal with that. Putting 2 electrons in at one time doesn't add up to 11. And so radicals don't form for us. Now, if you wanted to see how we get by with that, yep, we can put 1 electron in. And so when we look at that molecule, it does have a structure. It doesn't mean that it doesn't exist. It does exist. However, radicals don't truly follow our idea of Lewis theory and Lewis structures. Another one that wasn't necessarily identified with Lewis theory is incomplete octets. Can't spell octets today, but that's all right. Incomplete octets are going to be with atoms that do not need 8 electrons. Primarily boron. Boron is our classic example of an incomplete octet because he only has 3 valence electrons. Now we'll see that it follows Lewis theory. We can draw a structure. It's just an exception to our octet rule that we said way up here. We want to distribute electrons to give an octet. Well, we don't need to for boron. Boron does make more bonds than hydrogen. Hydrogen only needs 1 valence electron to complete its duet. Boron is special. When we think about boron, we can say he brings 3 electrons to the table. Each of our hydrogens brings 3 more. Notice we won't reach an octet. An octet is impossible because we only have 6 electrons. And so when we see boron in this form, we know that an incomplete octet will be found. Anytime you see boron, he doesn't need his octet. He can have one. We'll talk about formal charge in a little bit. But with boron in its neutral form, he's quite happy right here. 3 electrons makes 3 bonds, incomplete octet. When we talk about formal charge on the next slide, we'll talk about why is that okay. Expanded octets also occur. Oh boy. With expanded octets, third row elements or below can expand their octet. Third row, fourth row, fifth row on the periodic table, all of those can do this expansion of their octet simply because when we are looking at their bonding, they have something special. And that, what we're going to see at the end of this discussion, are going to be those d orbitals. So I'll have a little bit of a spoiler for you right now, just so that we can explain why the third row and below can do this. The one that I'm going to look at is going to be H2SO4. Actually, let's do this one first, because I like H2SO4 for my next example. With H2SO, or with SF6, sulfur hexafluoride, sulfur goes in the middle. He makes the most number of bonds. Typically, he would make 2 bonds. That's what we would predict he would need to make. But what we see here, when we count up the valence electrons, my 7s are funky, is that we get a ridiculous amount of valence electrons. And so technically, the total number of valence electrons here is 48. We'll see quite a lot of dots. Now, fluorine is in row 2. Fluorine can never expand his octet. Sulfur can expand his octet because he has the miraculous n=3 principal quantum number for his outermost shell. When we know n=3, L could equal 0, 1, or 2. And so technically, even though sulfur's valence electrons only go up to the p4, the 3p4 orbital, we still have the d orbitals available. So 2, 4, 6, 8, 10, 12 electrons go into bonding. The other ones go into the non-bonding lone pairs on the fluorine atoms to fulfill the octet. When we look at this expanded octet, again, we'll identify in our next slide why it has to do, for both of these, why these still work. Incomplete and expanded octets still work simply because when we look at the resulting structure, we get to double check with something called formal charge. Resonance and formal charge are 2 additional concepts to write the best Lewis structure possible for a large number of compounds. Now, for a large number of compounds, primarily the ones that have a lot of electrons, like our last one, when we get up to 48 electrons, the idea of double and triple and expanded octets becomes more readily seen. Resonance is used when there are 2 or more valid Lewis structures, and we can start to identify which one's the best, or are they equal. Namely, that comes when we have double or triple bonds. Formal charge, which is what we'll talk about first, we'll be able to use for any structure that we want to determine if it's correct. It's a bookkeeping that allows us to look and say, did I do everything correctly? What we want to be able to see with formal charge is that we've distributed the electrons evenly based off of the element. If oxygen brings 6 electrons to the table, did we give him 6 electrons in the structure? If carbon brings 4, did we give him 4? Things like that. And so formal charge, even though the molecule itself is not charged, a formal charge can tell us that there are charges existing in the molecule, they just overall add up to 0. We'll start with formal charge. The concept of formal charge is useful because it helps distinguish between competition and skeletal structures, or even competing resonance structures. And we'll see what resonance is in just a little bit. In general, these 4 rules apply. The sum of all the formal charges in a neutral molecule must be 0. So if I had a neutral molecule, which I'll show you in just a little bit, however, it's even though the overall charge is 0, that doesn't necessarily mean that there aren't any formal charges. Overall charges of +1, -1, +2, -2. We tend to see smaller charges. +1s and -1s are very common. If you start seeing the +2s and -2s, then you might have done something weird. But overall, formal charges should equal the charge of the overall molecule. So that's number 2. If we have an ion, a polyatomic ion is what we're going to be able to see in our examples. The sum of all the formal charges of the ion must be equal to its overall charge of the ion itself. Small or 0 formal charges are better than large ones. Zeros and +1s or -1s are better than +2s or +3s. When a formal charge cannot be avoided, the negative formal charge should reside on the most electronegative atom. And that's what we'll be able to say in resonance structures. Can we start to distinguish differences? Overall formal charge is calculated this way. The number of valence electrons that the atom brought to the table. Again, it's based off of individual atoms in a Lewis structure, minus the number of non-bonding electrons. These are our lone pairs. So add all those up, and 1/2 of the bonding electrons. This is how your book uses it. I also tend to just say count 1 for every bond that we have. So we'll practice. I like looking at this one first. Ozone. We've talked a little bit about ozone before in class. It's that molecule in the atmosphere that is currently depleting due to climate change and greenhouse gas effects and all of those lovely atmospheric chemistry topics that we can talk about. Overall, O3 is a neutral molecule. There's no charge up here in the top right-hand corner. We can add up all of the electrons. 3 oxygens means 18 electrons total. I put 1 oxygen in the middle, put the other ones around it, and we distributed some electrons. Now, this is the Lewis structure that I came up with, but what I see is that there's a lot of different looking oxygens, and is that okay? Let's just make sure that everyone has their octet. The oxygen on the right has 1, 2, 3, 4 lone pairs, 1, 2, 3, 4 bonding electrons, octet. And if we checked all the other ones, yeah, we have an octet. Now, when we look at these 3 different oxygens, though, we see something quite different. This oxygen has 2 lone pairs and 2 bonds, a double bond. This oxygen has 1 lone pair and 3 bonds total, a double and a single. And this oxygen has 3 lone pairs and 1 bond, a single. So now what we're going to be able to do with formal charge is be able to say, well, is this the best? Does this make sense? Did I goof? Did I mess something up? All 3 oxygens look different, so they should have a different electronic effect on each other. And so let's start with the one over here on the left-hand side. Formal charge for this guy is equal to the number of electrons brought to the table, that's 6, minus the number of lone pair electrons, 4, minus 1/2 of the number of bonding electrons, or just the number of bonds, 2. Overall, a 0 formal charge. Does that make sense? We know that oxygen typically makes 2 bonds. And that is what we see here. So this should make sense as a formal charge of 0. This oxygen on the left is neutral overall because he has his typical bonding. He had brought 6 electrons to the table. We've distributed 6 electrons evenly around him, 4 lone pair electrons and 2 electrons in the bonds. Now the middle oxygen, for his formal charge, he brought 6 electrons to the table. He owns 2 electrons in that lone pair, and he owns 3 electrons, 1 from each of the bonds. That overall 6 minus 2 minus 3 is a +1. So right up here, we would put a +1 above that oxygen. He has a +1 charge. That's not a delta. That's not a partial. That's an actual +1 charge. What does that mean? In this Lewis structure, we have polarity. We actually have in here an unequal distribution of electrons, which causes a charged area. Last oxygen, the one on the right, he brought 6 electrons to the table. He has 6 electrons in lone pair electrons and 1 bond, -1. -1 over there on the top. Now, these charges have to be written. Formal charges absolutely always should be your last step in determining a Lewis structure. You have to do it for every single atom so that you know the actual charges on those atoms. When we look at those charges, you need to put them somewhere around the atom that they belong to. So when we're looking at an alternate view of what this molecule could look like, we don't have to write in zeros, thank goodness, but any non-zero formal charge we do have to write in. You can write it on the top, you can write it on the bottom, you can write it on the side. You can even not write the ones, right? If you want to just do that. Sometimes in organic chemistry we circle them. That's okay too. When there are more than one, you have to write the charge for them. The value +2, -2, you would have to do that. But these are just alternates for us. The other one that I want to talk about is SO4 -2, the polyatomic. When we look at SO4 -2, sulfur and oxygen belong in the same family. So when we think about their typical bonding, each one typically makes 2 bonds. So who gets to go in the center? Well, when we think about sulfur being in the 3rd row, we know expanded octets can occur in the 3rd row. And so sulfur gets to be put in the middle due to that reason. Now adding up 6 electrons times 5, that is 30 electrons. One other thing why I like this example is this -2. The polyatomic ions give us a molecular formula that's charged. You have 2 extra electrons when you have an anion with a -2 charge. So think about what that charge means. A -2 means you have 2 more electrons, and therefore 32 electrons are there. We'll do 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. I'll double check and say, yep, I've gotten all of my octets. Everybody has an octet, but let's look at formal charges. All the oxygens look the same. So if I calculate one, I know the other one. And it's going to be the same from up here. It's going to look like the guy on the right-hand side when we had 3 lone pairs and 1 bond. Same formal charge. Those repetitious things should be noticed. Oxygen brought 6 electrons to the table. It owns 6 in lone pairs and it owns 1 in bonding. So there's a -1 charge on all of these oxygens. Well, I knew I was probably going to have some charge, but my goodness, there's some -1s all over the place. Now for the sulfur, formal charge here, sulfur brought 6 to the table. It owns none in lone pairs, and it owns 4 in bonds. That's a +2. Yikes, yes, that adds up overall to -2. However, we know that this probably doesn't make a lot of sense because we like formal charges of 0. We hope that we put in the right number of electrons. What formal charge tells us here is that even though it might not have been obvious, sulfur needs to expand his octet here. This is not always the case. Formal charge of sulfur is the main idea here. Being a +2 should be a warning sign that this is not a valid structure. So instead, what we should do is start sharing electrons. When we start sharing electrons, what we actually end up doing is changing the formal charge. And we start to decrease the number of formal charges existing in our structure. Here, when we donate and have 2 double bonds, one between the oxygen on the right and the oxygen on the bottom, again, I just chose 2. All of them are oxygen, so any 2 you want to choose. It removes 3 formal charges, namely the +2 from the sulfur and the -1s from those 2 oxygens. Now we have only 2 atoms with a formal charge, and those are the top oxygen and the left oxygen, both with a -1. This is important. This is the best Lewis structure we have because when we look at the count of formal charge, we've reduced the count by redistributing some of those electrons within the structure. We still have octets for everyone. We just now see that the expanded octet notion stabilized the molecule by removing some of the formal charges. We'll bring SO4 - 2 back again when we talk about resonance right now. Now, resonance structures have the same connectivity, meaning the same atoms are connected, just only difference is that single or double or lone pair counts can change. Resonance structures must have the same number of electrons. Second row elements have that maximum of the octet roll. Third row elements can have expanded octets. Formal charges must total to be the same. Now, if the resonance structures have the same formal charges, then we just call them equal formal charge or resonance structures. And we'll see that with SO4 - 2. I'll show you a couple of different options that we could have drawn. But if you start seeing that some formal charges have fewer, or some resonance structures have fewer formal charges, then what we can start to see is that some resonance structures are going to be better than other resonance structures. The best example that we have is looking at SO4 - 2 first. So if we pop down and bring our example right back here, a lot of you could have probably said, well, why did you choose these 2 oxygens? Was there a reason? And the answer is no. I could have chosen any 2 oxygens to make my formal charge decrease. So if you drew this structure for SO4 - 2, you would have had what we call a resonance structure. Polyatomics are one of the easiest ways to draw a resonance structure. It's an alternate structure that says these are identical. I'm not going to use a yield sign. I'm using these double-headed arrows as my resonance arrows to say any two oxygens, doesn't matter which two I choose, any two oxygens can have that double bond with the sulfur. And the other two oxygens will have the formal charge of -1. These are all equal resonance structures because every one of them has two sulfurs double bonded to oxygens and two oxygens with -1 charges. So there's nothing different about them. So we'll call them all equal, and even you can draw more, right? There's going to be multiple different variations of this one.